thank you so much to all of you for coming. I'm feeling really flattered by this crowd. You guys must have really good cookies. So yeah, what I'm going to talk about today is some of the things that we think about in my research group and with my collaborators toward a sustainable energy future. Okay. Just have to acknowledge some of the people that I work with and some of my funding agencies. These are a couple different shots of my research group and some of the people that I collaborate with, both internally and externally, and some of my funding agencies. So and anything that I say here that is correct is because of good work of my students, and anything that I say wrong is completely on me. Okay? Okay, so the requisite outline slide. I'm going to just give a little bit of background on why renewable energy is important. I'm assuming that most of you know this. But I also would be remiss if I just jumped right in. And then why can't we just jump right into renewables? What are some of the challenges from a technical perspective? How are we going to integrate it? And then Laura asked me to talk about just a couple of projects specifically. So I chose two very different projects to highlight in a little bit more detail today. If at any time during my talk you have questions, feel free to interrupt. I love to have a little break while somebody else talks for a minute. And then it'll break up some of my discussion. I'll try to leave a few minutes for questions at the end. Okay, so climate change is for real. We can clear that up, right? Okay, it's for real. The important point being that if we're really, really good and we play our cards really right, we're still going to see some global warming, but it's not going to be as bad as the red side on the, my right? Over here, which is the sort of worst case, business as usual. We just keep, doing what we're doing and don't try anything at all, right? So climate change is important. Bad things happen. We all agree. There has been, you probably have seen the IPCC reports that talk about what do we actually need to do to keep global warming to within 1.5 or 2 degrees C long term. And that the reason we might want to do that is if we keep it in this band here, right, we're still going to see moderate risk due to climate change across many, many dimensions of our world, but at least we're good. That's about as good as we can do. Okay, we can't avoid it, but what we can do is try to minimize it. Okay, and that's what we're going for. It turns out that actually I have a friend and a colleague who was on that IPCC report, and she says it's dire. It's going to be almost impossible to do this, right? But we have to figure out how, and so to do the best we can to get there. The important point being that to keep it below 2 degrees, we're not only going to have to do sort of our conventional abatement technologies where we, stop relying on coal and natural gas, stop using fossil fuels, right? I'm focused on the energy industry because it is the largest contributor to this whole problem, and yet a fundamental underpinning of our society, right? So it's a bit of a problem. But not only are we going to have to deal with this kind of stuff, we're also going to have to figure out how to get some negative emissions, right? We're going to have to take some of the CO2 out of the atmosphere and pull it out because it's kind of too late, right, to do it all just by changing our behavior. But that's not what I'm really here to talk about today, but that's just sort of to set the stage. I think I showed a couple of these slides the last time I was here, but the point I want to make here is that energy is the issue, right? If we can solve the energy issue, then we're so far ahead. Okay, so I'm focusing on energy here today. Most of the states and cities in the last year or two now, I guess, have been making sort of their own commitments, right, to dealing with this problem. I'm sure, I know there was a bunch of people from Dartmouth that went to the COP meeting last year and the year before, where they talked about, the we're still in movement, right? So despite, moving out of the Kyoto Protocol, a lot of the cities and states are staying in there, and a big part of that is how we're going to deal with the energy issue. New York State, you probably know, has made huge commitments over the next 15, 20 years I come from New York State, right? To get rid of carbon and become completely carbon free. The problem is that we just really don't hear much about how we're actually going to do it. All right, so consumption, renewables share of energy. So renewables is the answer. The question is, how are we going to do it? So I talked a lot about how important energy is, but I think it's also interesting to understand what we use that energy for. So this is renewables' share of energy consumption by sector. And so 51%, right, of the energy we use is actually for heating and cooling, right? And that kind of has it would require a shift, right, in how we heat and cool, right? So talking about electrifying things, right, which some communities think is a silver bullet, right? We can decarbonize our heating and cooling by electrifying it. Maybe, if we decarbonize our electric system and prepare for all that load. Okay, so there's a huge burden here, right? And the bulk of it is actually non-renewable. Transport's another big problem, right? And again, the answer very often is, it's okay, we'll electrify it. So we're going to electrify everything, and then it's going to be carbon-free. Okay, so getting carbon-free electricity is challenging, as you probably know. I'm probably going to tell you some more about that in a minute. And then if we're going to get this carbon-free electricity and take all our heating and cooling and transportation and plug it all into that system, right, it makes the problem even bigger. So can we agree it's non-trivial? Okay, move on, Lindsay. Okay, so wind power is growing, solar power is growing, right? This is from the end of 2017, so we're getting a lot of this stuff. The question is how to integrate it. I'm not going to talk too much about that, but I do want to show you these because I think they're really cool. This is from a New York Times article called How Does Your State Make Electricity? Has anybody seen this? So you can flip through like all the states, and I stumbled across it in the New York Times, and I thought, oh, I have to share this. So this is from 2001 to 2017, and this is New York. And it just gives you a really quick visual of how the energy mix in the state has changed over time, right? So this is just for fun. So this is New York. This is California. Okay? Still quite a lot of natural gas. West Virginia. Yeah, right? I saw this. I thought, how could I not put this on a slide, right? Yeah. Okay. And then, of course, Vermont. I thought I had New Hampshire. I lost New Hampshire. I'm sorry. So this interesting thing about Vermont is that a lot of hydroelectric, but you know Vermont only produces a third of its own electricity? Right? So a lot of that is actually being imported from the north. So anyway, I thought that was kind of interesting, in particular when you look at New York, right, where natural gas went up and came back down and went back up again, right, around the time that natural gas became really, really cheap. Okay, so that was just for fun. All right, so why can't we, and the last time I was here, I spent probably a good 20 minutes talking about, you know, look, we have all this wind, look, we have all this solar, look, we have all this geothermal. Why are we not already there, right? So I'm not going to make that whole case again, just a little bit, but there's both technical and social challenges here, right? And some of them are the same, right? So on the technical side, we have to deal with the uncertainty and variability if we're going to go completely to renewables, right? These things are non-predictable, or they're hard to predict, and they change all the time. They're not necessarily located where we would like them to be, right? So we don't want to put wind farms right in New York. Well, we can't put wind farms in New York City, right? But that is exactly where the load is, right? So if we're going to build large wind farms, large concentrated solar, like utility scale things, they're going to be far out, and then we have to build transmission to get them in, okay? Infrastructure is always challenging, and then there's always the question of transportation and heating. On the social side, there's issues around uncertainty and variability socially, right? People are uncertain what's going to happen if you put a wind farm or a solar farm near their home, right? They're concerned about that. So siting becomes a problem. Regulatory, there's risk there. People are concerned about, well, just because I have this incentive now, you know, what if it goes away, right, in terms of utilities investing and so on. And that means that the economics are always changing. So the point of this is that the challenges of the energy transition are not only technical, though I'm going to focus on the technical for a little while. Okay, so this is, I'm going to make a case for why the uncertainty of renewables causes a problem. And this is sort of my exemplar timeline of how an energy market might work. Okay, depends. There's variations between a deregulated energy market, an ISO, vertically integrated, right? But in general, there's a time scale that these decisions have to be made. So we start, this may or may not be, yeah. So we start sort of day ahead, right? And we look, if I'm the system operator, I say, oh, okay, so I know that tomorrow's a Tuesday, and I know what the temperature is going to be. So I have a pretty good guess of what that load profile is, right? How much energy I need to provide. Because rule number one of operating an energy system is that demand and supply must always match, right? So I have to be really good at predicting how that's going to work. Okay, so I decide how much I'm going to need. I decide which units I'm going to commit, right? So if I have a portfolio of generating units, I have to decide by some sort of optimization algorithm, I have to decide which ones are going to be on, right? Because I can't flip them on like a light. So I have to decide ahead of time. They have a certain amount of time to come online. They have a minimum output level once they're on, right? And they have a maximum. So you make some decisions based on these forecasts and also what those generators are going to charge you or what you have to pay them depending on your market style, right? So those decisions are usually made the day before, hour-by-hour basis on forecast. So then, and remember, forecasts are getting more accurate, right, as we get closer to the observed value, right? So 24 hours ahead, there's still quite a lot of error there. And then we get into the day, right, and sort of hour ahead, we're going to update for anywhere from an hour to 15 minutes ahead, depending on what market you're in. We have to update those forecasts for our wind, for our load, temperature, solar insolation, all those things, right? And then we sort of re-optimize the system, but now we're constrained to the set of generators that we decided on the day before, right? So you can see here that now you're becoming more constrained on what you can do. And so now all you can do is say, oops, I made a mistake. You ramp down, you ramp up. There's congestion over there, right? And sort of tweak everything the hour ahead. Okay, and then in real time, we have some reserves that we planned on, right, to cover any shortfalls. And those reserves can be up or down, or any other contingency, like some generator went off, some line is congested, and so on, right? So there's a lot of moving parts, and you don't even know your prices till afterwards. Okay, so you're wondering why I told you all that. I'm sorry. The important thing is that we have variability going, we have uncertainty in many stages of this decision, right? So we have to decide different things before we have full information, and we don't want to undercommit or overcommit, for example. Okay, so this is just some, to make the case for why wind is challenging, right? So this one up here is just a sample time series of wind, right? So it's highly variable. And then this is not my beautiful chart, it's somebody else's beautiful chart, but it shows you the forecasted wind output, right, over 2 days, essentially, and with confidence intervals. Okay, so this is the expected wind. These are confidence intervals. You can see that when you're forecasting 48 hours ahead, they're really, really big. And the actual observed, when it actually became observed, was kind of in there, but still bouncing around all over the place, right? So it's really hard to make advanced decisions on those things. And then I was talking to somebody today, and I said, I'll show you the duck curve today. So how many people have seen the duck curve? Almost half. Okay, that's good to know. So because I was having this conversation, I was like, oh, everybody's seen the duck curve. So basically what this shows you is this is a sort of a contrived example from California, that this is the load, right? And then this is the net load, which is load less solar generation on the system, right? And the point of this is to say, wow, like we're okay when the sun's not shining, but as we get more solar on the system, in the peak of the day, we're going to have this huge dip, right? Which, at first glance, you say, that's okay, because we just need less energy. But remember I said that we committed these generators the day before. And once they're on, they can't go to zero necessarily, right? So this need to ramp down a whole bunch of generators all at the same time really quickly is super challenging for the system, just as challenging as it is to ramp them back up, okay? So coming back to our previous diagram, whoops, this one, right? So what happens here is we're taking these forecasts. I guess I should have put an arrow here as well. But we're introducing all this uncertainty each stage, right? And that uncertainty is not resolved until it's too late. Well, not too late. I mean, we have reserves and we can balance things, but the uncertainty is not resolved until, you know, much later in the actual system operations, right? So the challenge with getting all of these renewable energies into the system is that we lose the flexibility of being able to adjust the other generators, right? So right now, 20% wind is really not a problem because we have all these natural gas plants that we can sort of just adjust, right? But the more we replace natural gas or nuclear or coal even with renewables, right? So you can see that the resources that are inducing this struggle are going to induce more of a struggle, okay? So I'm not saying we shouldn't do it. I'm just saying it's not an easy problem to solve. Okay, any questions so far? Yeah.
I don't know the first thing about energy generation.
Okay.
But can you give me a bit of intuition for the scale spatially at which these generators operate? I have the feeling that if you were to scale down to, say, a smaller area, you would need less fluctuations, and you could account for renewable energy a little bit better just by having less power localized to a particular place from generators. And I understand that doesn't seem to be the case.
So I'm not quite sure that I'm understanding your question, but I think what you said was if we distributed them around, then there would be less uncertainty, right? And that's actually true, right? So one of the solutions for sort of smoothing not so much the solar, right, because day and night, but for smoothing the wind would be to distribute it over very large geographic regions, right? So that the weather patterns that you're seeing at one place are not necessarily being seen in another place. And so like finance, right? So you're diversifying your portfolio and you sort of mitigate some of that volatility. Yeah. So that is a true thing. The distance at which you have to space these things is hard, right? So it's really big, and then we have to build transmission. And so it'd be great to have small distributed things around, which is a really good way to go. The challenge with that is how do we manage a bunch of distributed resources, right? So it's not that it can't be done, and it's coming, right? It's this decentralized optimization piece. And then also the siting, right? So siting these things at many, many places is hard, and then you also lose some economies of scale. So your idea is actually right on track, and we do have to go this way. There's also challenges associated with that. Yeah. Okay. All right, so to talk about some of the things that we've been doing, so that sort of leads us to the overarching goal of my research program, which is supporting this transition in any way we can, okay? So I started in this place basically as a power system optimizer, right? I said, you know what we need is better optimization algorithms under uncertainty, right? Stochastic optimization to make just better decisions of how to operate our grid, how to make those commitment and dispatch decisions better. That's where I started. But it turns out that there's a whole bunch of different pieces. So some of the things that we've done, we have worked on stochastic unit commitment and dynamic programming models and some robust optimization to try to explore different ways to incorporate the uncertainty in the optimization models depending on the application. We have done some work on storage. I'm going to talk about storage next, because the storage problem actually introduces a whole new dimension of complexity into these decisions. So the market that I was telling you about just now said nothing about storage. And I think we know sort of intuitively, right, just looking back at that duck curve, that if we could store that energy when the sun is shining, no more duck curve, right? It wouldn't be a problem. But actually managing a grid that has multiple storage units distributed around is actually really challenging. So I'm going to talk about that a little bit. We've done some work at looking at the impact of, for example, the Clean Power Plan. What would happen if we actually implemented that kind of a policy on a grid? And we did some simulations to look at sort of how the different components of the Clean Power Plan could work together. and work on actually characterizing the uncertainty and doing some scenario reduction on renewable resources. So obviously I can't talk about all those things today, so I picked two things. Okay, and the first thing I'm going to talk about is incorporating storage into operational decisions, and then the second thing I'm going to talk about is multi-objective optimization for microgrids. Okay, so the first project, I'll just skip that part. I can talk about this really quickly. So this is essentially the same diagram, made a little bit simpler. I have no idea why it's got an X on it. But basically this idea that we put in our inputs and our forecasts, we make the unit commitment decision, we update it with information, and then we sort of do a recourse stage where we update some things. So power system operators have been doing this for decades, right? This is what they do, right? They model the grid, they make optimization, cost minimizing decisions. So what I want to tell you about is why storage changes things, right? So it's all an optimization problem, right? Optimization problems have an objective. We're going to minimize cost. We have constraints. We're going to make sure that the supply and the demand matches all times. We're going to make sure that we know our generators have upper and lower limits, lots of different constraints. We have transmission constraints, but they're very static, right? So if we know what we have for this hour, we can just, even if there's uncertainty, we can make an optimization decision. And they're not necessarily really linked to the next hour or the previous hour, okay? But when we get into things like ramping constraints, right? So this is, my generator is putting out at 100 megawatts, right, this hour. How much can I put out next hour? What are my limits, right? So then you have to start thinking about intertemporal constraints. Storage makes this even worse, right? Because storage is the silver bullet, don't get me wrong. Mathematically, it makes it worse, right? Because now you have an opportunity cost, right? So if I have a gas generator and I'm making a decision how much to generate in the next hour, the only thing I care about is, like, what's the most I can ramp, right? What's the lowest I can go? But I just have to feed it fuel, right? And that doesn't mean I can't feed it fuel next hour. If I have a battery and it's full, when I try to decide if I want to use it the next hour, I have to think about, well, what if it's only noon and the peak when it's going to be worth the most money is at 3 o'clock? So maybe I wait, but it's 3 o'clock and I think, oh, maybe 4 o'clock, right? And so you really have to really look ahead. And so that completely explodes the dimensionality of the problem. Right? Now I can't really make a right now decision. I have to make a forever decision. Not really, but Okay, so that makes it much harder. Skip that. So when we think about representing wind uncertainty, typically what people want to do is use a scenario tree, right? So this is how much wind I have right now, and an hour from now I could have this or this, right? And an hour from then I could have this, this, or this. You see where this is going. Right? So if I want to model this hour to next hour, I can pretty easily discretize that space, right? But if I want to follow that through for 12 hours, explosion, right? In the computational challenge. Okay, so what does this problem look like mathematically? So this is a standard optimal power flow problem under uncertainty, okay? What does this say? Well, this says, I think I saw a pointer, did I? This is a pen, isn't it? Okay. Okay, so we're going to minimize some cost, right? And this could be, well, except for these words right here, this could be for any optimization problem under uncertainty, right? I want to minimize the expected cost, right, over big T time periods, okay? And so I'm not even going to say what that cost function is just yet. We'll just keep it general. Like any optimization problem that's based in reality, we have some constraints. So this is the power balance equation where I said your supply has to equal demand always, right? So this is how much I'm generating, how much I have to provide, and let's just say we have some wind, right? I also have power flow equations, so how much can flow, and you can picture this spatially on a network, right? How much power can flow through the lines at any given time. Storage dynamics, right? So this is the key one here, that you can't sort of overdraw your storage, and it has a limit how much you can store. And then you have some sort of bounds on like ramping constraints and decision variables and things like that. Okay, so this is the part that I already told you, that storage dynamics makes it really hard. And we're going to structure the decision like this, pretty straightforward. We're going to take our current state, right? This is just a visual representation of the optimization model I just talked about, right? So we take our current state, we put in our new information, we make some sort of decision, we transition to the next state, then we go around that circle. And the things that we care about, right, the relevant information at each time period is the level of storage, how much I was generating in the previous time period. Remember, I have ramping constraints. What's my wind forecast? What was my past wind output? Okay, so when we now put this into, we put storage dynamics in here, what we end up with is something like this. Okay, and for those of you that have looked at dynamic programming, many of you I'm sure have, you know that what we're talking about here is that the cost of this decision now, right, is the cost minimizing decision, so the cost minimizing decision of whatever I do, that first term, plus the expected cost for the rest of my time, right? And so in that red part, that's where you have to figure out what the value is of every decision from now to the end of your thinking time, right? So maybe that's the day, right? Same constraints, right? So in dynamic programming or stochastic dynamic programming, you call this the cost to go function from the period now where you're making the decision until the end of your horizon, right? The trick is there's two sources of complexity here. First of all, computing expectations is hard, right? It's computationally very expensive to compute a true expectation of something. And the other thing is that this state here, right, to here requires you to do it exactly, right, would require you to make it, to do an optimization for every state or every possible state from here to the end over that growing tree, right? So the traditional way of solving this kind of a problem is stochastic dynamic programming, which I'm just going to show you because I love this. Typically, when we do stochastic dynamic programming, we just discretize the space, right? We say, if I don't know what that variable is going to be, but I know it's going to be between 0 and 10, I'll just say it could be 0, 1, 2, 3, 4, 5, right? I'll discretize it. And then I'll say that's good enough, and I'll optimize over all those points, okay? This little grid here, which actually means nothing, except to show you that this has 20 points discretized in dimension 1, and it has 20 points discretized in dimension 2. And so that's actually it's a small problem, 2 dimensions, right, with a small range in each of those dimensions. And you have to compute the optimal solution at every one of those grid points, right, which is absolutely doable in this problem. What is not doable is this very small energy system problem, right? 5 wind turbines, 5 storage devices, discretized into 10 levels each, okay? This is 10 to the 15 grid points for every time step. It can't be done, right? So, and this is all because we introduced storage. Because before storage, we only cared about the previous and the next. And now we have to look forward if we're going to solve it properly, okay? And we're going to have these storage units all over, right? We should. And so when they're distributed around, we can't make them all do the same thing. That would be totally inefficient, right? So to use storage properly, to get the economic value that will justify its existence, we have to use it properly. Okay, so what can we do? Oh, this is more about the curse of dimensionality because big numbers are cool. So if we had 15 storage units all discretized into 7 levels, which is not a lot, that's how many optimizations we would have to compute.
proportions were not that hard to calculate, so that it's going to be a interval that all of the proportions are going to converge to a number, so that we have a sort of stable and stationary status.
So I would say it's not stationary. Okay, and so you can definitely do some approximations, which is what we're going to do to try to get at some of those answers. So I don't know the detailed answer to what you're asking, right? So you could compute proportions, but remember we have to make very detailed decisions with those things, right? So, but this is the thing. This is where these solutions come from. Somebody says, yeah, but couldn't you try that little trick? And then somebody tries that little trick and it works, right? So that's where most of our cool optimization things come from, like this one, where I'm going to talk about pretty quickly about how we can solve this problem. Okay, and this is not our technique, developed a long time ago using ideas from Bender's. And basically the idea is you don't discretize in space, but you sample, and then you use the samples, you do the optimization on those samples, and you use it to construct an approximation. And then you go backwards and you test your approximation, and you go forwards until you converge. It's been used fairly successfully in hydrothermal system management, where you have multiple reservoirs, and it's a similar type of problem, right, where your reservoirs have storage and you have to make some of those decisions. So anyway, and I said it, so what you do is you basically sample a forward phase where you sample the state space, develop your approximation, and then you go backwards and you test it and then refine it, right? And you iterate back and forth. And this is all you need to know, okay? So this is just, again, like a stylized little visual, right, in 2 dimensions, and we're talking about very many dimensions. But the point is this, right? So the expectation was where all the challenge was, right? The expectation is hard to compute, and you have to sort of do that whole exploding thing, right? So if we can get rid of that, then we're good. So what we do, we assume it's convex. We can talk about that later for those of you that want to. But if you assume, this only works if it's convex. And what you do is you compute a lower bound, right? So if this is your actual cost to go function that you don't know, you can basically make a piecewise linear function, right, by the tangents to that convex function and construct an approximation. Okay? And we kind of know, well, we do know for sure that the best guess of that is going to be the upper bound, right, of those linear functions, right? So we're going to get a piecewise linear function, and we also know what the parameters of that approximation should be, right? Because we all took first-year calculus, and we all know that the slope of these piecewise linear functions come from the derivatives, right? And we know what the important derivatives are, right? It's the dual variables from the optimization. Okay, so I made a weak leap there, but the concept is correct. Okay, not mathematically, I mean in my explanation. Okay, so we know that we can construct this approximation from these dual variables on your different functions, right? So on the wind production, on the generation decision, right? And your cost functions and your storage decision. Okay? And so and then you have this really nice linear function, right? Upper bound of that linear function, and you replace your hard part with that nice little function, and it actually computes really fast. That was there just in case people had questions. We can come back to it. So first thing you do when you make an approximation is you test it and see if it works. So we took everybody's popular 9-bus network, and we took that one because we can do the stochastic dynamic programming calculation on that one, right? So we can use that to say, this is the ground truth-ish, and how well does our approximation work? So we do that and compare that, and then I'll show you some tests on a larger system to convince you that it kind of works. Okay, so this is the IEEE 9-bus system. It's a network that represents a 9-node power system. Okay, and it comes with known parameters. People know how people know how it behaves, and this shows Two examples. One of them, this is the net load. So it's the total energy we need minus the wind or solar that we had. And this is the storage level. And this is the case where we have batteries that are actually really inexpensive to charge and discharge. So they're quite efficient, right? And this is the other important thing here is that if you have multiple distributed batteries on your system, they're not all going to have the same characteristics, right? So you need to be able to model those differently. So this is just one battery because we're doing this sort of validation step. The battery starts empty in this case, right? And so it charges up while load is low and then discharges while load is high. Not rocket science, right? That's what it should do, but it does. So that's good. This is the case, same model, different load profile, and charging and discharging is expensive, right? So you lose a lot. Oh, no, I'm sorry. It's still cheap. And this one, it starts full. Okay, so the first one starts empty, this one starts full, and it holds on to the energy until it needs it. It's still inexpensive. Okay, and then discharges right away. And this is the case where it's really expensive, and it starts with some energy, but it really kind of holds on to it and doesn't charge anymore here when load is lower because it's just not worth it in the optimization. Okay, so let's be honest. The results on the IEEE 9-bus system, they don't really map to reality, right? So we need to look at bigger systems. But the important thing is that we want to make sure by solving the actual stochastic dynamic programming problem that the approximation algorithm that we're using actually works. So, okay, it's faster. This is faster, okay? 10 minutes or 30 minutes versus 3.5 hours. And then this compares the average solution across. So this is the approximate, and this is the exact, approximate exact. Run 2 takes a lot longer and is more accurate because we did a lot more discretization. Okay, so it's a finer mesh. Okay, it's not actually mesh. We did more sample points, right, in this version. So it takes more time, but it's actually surprisingly accurate. Standard deviation of the solutions are pretty similar. So that's just to convince you that the method actually works. Okay. Yeah. And then we wanted to test it just on, because the whole point was larger systems, right? So we tested it with 5 different batteries on the 118 bus system. We had 2 inexpensive storage units, 1 that had very low capacity and 2 that were really expensive. This one that has low capacity obviously can't do very much. These ones get used a lot because they're cheap and the other ones get left out in the cold. Okay, exactly what we would hope would happen. There's lots of other tests in the paper that I'm happy to share with you. The important point is that solution times are actually really reasonable, even when you get up to a 300 bus system with 20 storage units and 10 wind farms, right? Which you wouldn't even attempt without an approximation algorithm, okay? So, and they don't scale particularly badly either, right? And with dimensionality problems in SDP, the computation time explodes really, really fast. So this has some potential for doing larger and larger systems. It definitely optimizes the trade-off between here and now and the value of future flexibility. We can handle the dimensionality. We can model every storage facility individually with its own parameters. And then you can also incorporate different correlations among wing sites. Okay? So it provides an effective dynamic optimization with reasonable accuracy. Okay, so that has some potential. Any questions about that? Yes?
You did mention about scale quite a bit, and I think the way you're measuring scale is, I guess, spatial in terms of the number of units. But what about time horizon? Because you briefly said something about maybe a day is a time horizon, but is that...
These are all 24 hours.
And is that practically making sense? I mean, you also talked about what if the battery starts being
Right.
charged versus it's not. And is it fair to say, maybe with solar it is, but is it fair to say in general that everything resets at midnight or something?
So no, but you could implement this in a rolling horizon model, right? So that you would sort of go forward through the day and sort of keep stepping forward and always do the 24 would be one way to do it. Yeah, but this is it's a 24-hour model.
And another
Yeah.
is talked about using this SSDP idea, which is there in the literature, and basically uses this kind of bender's cuts, right? So what's the big challenge in bringing that to sort of this
energy context, what is there, like, what's the key ingredient there?
So the key ingredient, so the SDDP part has been used before, but not in energy systems with that kind of scale, right? And the other thing is that it incorporates the actual power flow optimization, right? So you've got your voltages and you've got your frequencies and all that at all the different nodes, right? So that hasn't been applied in that context. So it's really the dimensionality problem. Yeah. Okay. So the next thing I'm going to talk about, of course, it's a professional hazard, right? I talk too long. So I'm going to go fairly quickly, but this is the reason I chose this project is it's completely different from the other project. So that was a very traditional mathematical optimization, right? We do numerical methods. We calculate approximations. It's traditional mathematical tools. And this is on the far end of the spectrum, still looking at energy problems. Now we're looking at a microgrid instead of a large-scale system. And we're going to use different tools. We're going to talk about multi-objective optimization, real multi-objective optimization. Okay? If you take one thing away from this section that I'm going to do really fast, it's that there's a difference between multi-objective optimization, the way many of us learned it, and true multi-objective optimization. And we're going to explore how we can sort of understand the trade-off, and we're going to use some evolutionary algorithms. Okay, so setting the stage for this problem, and this is things that we've seen before in this talk, even that the whole idea of power system decision making has been based on minimizing expected cost, right? But what if we have other objectives, right? What if we want to minimize our environmental emissions? What if we want to maximize the reliability of our microgrid because we're islanded from the main grid, right? What if we want to include those things? So traditionally, what we've done, I'm going to skip some of this. Oh yeah, no. So traditionally what we've done when we try to do multi-objective optimization is we try to just cram it all back into that other optimization formulation that I showed you, and we say, well, cost is, in here, and then we'll just apply some kind of financial value to our carbon emissions, and we'll put it in there. Or maybe we'll just put, and if they're not equally important, we can weight them. But we're going to put them all into one dimension, and we're going to decide a priori, that's going to come out weird, what our priorities are. Okay? We're going to decide how they're relatively important to each other or not. Okay? And this is not what we want to do. Because if you do this, you're linearizing this objective function. You're missing some nonlinear relationships. You might be missing good solutions that actually do better across these dimensions than you knew about, right? So you want to not maybe make those decisions ahead of time. Okay. Is there anything here? So what we want to do is we want to minimize cost or minimize negative revenue, minimize negative reliability, which is maximizing reliability, and we want to minimize emissions. We have storage. We have different boundary grid states on our generators, right? Decision variables are how much to generate, how much to buy or sell from the grid if we're connected. Okay, we don't have to be connected, but we can be. Traditional optimization methods don't work here for this multi-objective problem, again, because the computation complexity grows in the number of decision variables and the number of dimensions. Okay, so we're going to try a totally different tactic this time, and we're going to move into evolutionary algorithms. So this is basically the idea of this is to develop a policy, right? To develop an operational policy that you can give to the microgrid operator that says, you already told me what your priorities are. Based on that, these are the policies you could use. If you know what your state of your system is, then you should do this, right? So we're going to we're going to really simplify the problem into a parametric policy space. We're going to combine multi-objective optimization with a simulation based underneath, okay, which is not something we've done before. At least I haven't talked about today. How's that going to work? So what you're going to do is you're going to have some sort of simulation model. So this is much easier than optimizing, right? You can simulate your system very quickly with some sort of policy, right? And then you can look, based on that policy, how well did it work, right? What are the values of my objectives? Is that a good policy? Was the last policy I had better across all those dimensions? Let's throw this one out then, right? And so you can cycle around until you get really good policies, and you can include all the nitty-gritty details you want because it's a simulation model underneath, okay? So I'm oversimplifying because the hard part here is how do you search that space, right? And that's where the evolutionary algorithms come in. And we borrowed some tools from, some ideas from, is it here? Hang on. From this particular framework, which was developed by another colleague at Cornell in a different department. And really what it allows us to do is use a whole bunch of different different sort of evolutionary algorithms where they reproduce in different ways. And the important part of this is that the weighting of how we evolve our populations is dynamic. So say I do equally select from these different crossovers in my evolutionary algorithm, right? So how do I pick new points to try? This is what all this is about. How do I pick more points to try? So I sample from all these different methods, and the ones that do better actually get more weight going forward, right? So dynamically updating how we select new places to search, okay? And there's a whole bunch of theoretical literature on how well these things converge, which we're not going to talk about today. But what it does is it lets you do the simulation-based approach, check your optimization, check how well it's doing, and then throw things out that aren't working, like the dominated solutions, and then sort of just keep looping around, right? And then you end up with a policy that has reduced number of decision variables, and you then sort of generalize to system states that you haven't observed, right? So it's another approximation, just a different way to get at it. And then what you do, again, this is like a high-dimension problem that you could reduce to a two-dimension, is you end up with some sort of policy that says, hey, if this is how much I have in my battery, this is how much I should generate, right? And you could, if you believed this policy, you could give it to a microgrid system operator and say, just do this, right? If you believe it and they're happy with it. Okay, and this is just sort of how we formulate them using cubic basis functions for the different dimensions that we're modeling in the policy. And there's no particular reason to use cubic basis functions. That's just the second or third thing we tried, and it worked pretty well. And so this is the same map again. You have inputs of wind, solar predictions. You run your simulation model with some sort of candidate policy. You calculate your objectives. You say, oh, how did we do? If we did better than we've done before, we keep it. If we haven't, then we throw it out. And we build basically a library or a database of these potential policies. Why? Why would I do that? Because I don't want to make any a priori decisions about what's important to you if you're running the grid, right? I'm just going to tell you these are the candidates, right? All of these were not dominated by others. Okay? All right. So I'll show you some examples. It's a microgrid that has one generator, one wind farm, one PV, not a one PV panel, one sort of community level solar, one storage unit, has an incoming exogenous price signal, and it has to make decisions about exchange between the grid and itself, right? So when to generate, when to sell, when to buy, right? Okay. We get to the meat of it. Okay, so we're comparing different frameworks. The important thing you need to know is that if we do sort of the typical optimization where we take the expected value and we optimize it, we get the blue dot, okay? And so this is sort of each of these solutions tells you a trade-off between curtailable load, so how much load did I shed, so we'll call that a reliability metric, and how much money I'm going to earn, okay? So if I only care about money, I don't need to do this, right? Because I would just go up here and take that one, which I can't because that's the perfect information, right? This is like I'm an oracle and I know what's going to happen. I could make that much money, okay? But one of the next best things actually is that blue dot, which is I just plan based on my expectation and I make a decision. So why are all these other things here? Right? So all of these are all different policies that you could choose. Right? And each of these are not dominated by the other on some dimension. Okay, so I still haven't made a decision for anyone about what's best. But it kind of looks obvious. Like, it seems like I should be able to throw some of those out, right? I should be able to throw out probably the conservative policy, except that if I care about reliability, I might not. But it doesn't look that great. But if we actually move into the emissions dimension, so now this is the same set of policies, but now I've included emissions there. And you can see why those policies are still there, right? Because for every one of those policies, it doesn't perform worse on every dimension than some other policy in that set. You're thinking, so what? Okay, get to the point. So the point is that now you can turn around to your policymaker, and this is actually how each of these policies perform on my 3 objectives, right? So if I really only care about money, I take that one, but know that I'm going to emit a lot, right? And I'm going to have moderate reliability. Okay? If I really, really, really care about emissions, I'm going to lose some cash, right? But actually, I can be fairly reliable, sort of. You can't, there's like 3,000 policies. No, there's like 1,000, okay? You would never give somebody 1,000 policies. But the point is, these are all candidates, right? And you could, as the microgrid sort of community organization or whatever, you could say, you decide what your priorities are. And you still wouldn't give them this much. But what you might do is do something like this, okay? So this is a filtered set of those same policies. But what we did was we did a sensitivity analysis, and we said, okay, so we came up with these policies with a certain level of uncertainty, right? So maybe plus or minus 10% for prices, plus or minus, I think it was actually like maybe 10% for load and 10% for wind and 10% for solar or whatever. And so we came up with all those policies, and we said, yeah, but what if we were wrong? So we didn't retrain the model, but we tested all those policies after we increased the uncertainty, right? So we said, okay, increase the uncertainty a whole bunch, and then sample possible scenarios, test it with all the policies, and these are the ones that are still viable, right? So you have a much smaller set, and you could say, oh, now you could kind of, if you're the decision maker, you could really choose from these, right? And you could use that to operate your system or to plan your system. And if it's not working, you can try another one, right? But you can now have an open conversation with stakeholders that says, what are our priorities? And you decide which one to choose, right? And it's not static. So you can actually change your mind, right? Or if conditions change, then you would do it all again. Okay, so you can see this is a similar context of problem, but it's a totally different approach. Okay? So with this, we sort of show that the multi-objective optimization is possible without deciding ahead of time relative importance, and does actually provide distinct results depending on what your perspectives are, which is really important as we try to get stakeholders more engaged in this energy transition, right? We can't keep prescribing the solution. You can get simple policy functions that can make decisions, and I didn't include those results, but we showed that if we scalarize the objectives, so if we just weight them ahead of time, that you miss so many of those candidate solutions that we had, right? So there are big gaps in there where this solution would have been much better and we missed it because we filtered ahead of time before making decisions. I will say, for the standard economic dispatch decision, the kind of thing we did in the first project, this is a terrible idea, right? This is pretty computationally expensive and is really for helping stakeholder decision making, for exploring these trade-offs. So it's a totally different problem, okay? But it allows us to explore different questions than we have in the past. Okay? We would never be able to solve a multi-objective problem with the traditional context. Just some things that we have going on with that particular project. I'm going to skip over that. And the point being, sort of wrapping up because I'm way out of time, so 2 sort of methodologically distinct projects. One that's really focused on the system operator problem and what are some sort of fun mathematical tools we can throw at it in the sort of traditional context. And then this is absolutely about community and stakeholder engagement and how we can take these complex decisions with all the trade-offs and sort of filter the decision down to something that makes good conversations happen, and lets us ask really good questions. And I think with that, I'm done.